Good afternoon, everyone. So, welcome to this uh, course. Welcome to the fourth week of this course titled Defects in Crystalline Solids, Part 2 by Professor Shashank Shekhar from IIT Kanpur. So this is a metallurgical and materials engineering course. So this is the fourth week of this course. So today in this session, so we will talk about, so this is the course outline for this session. So this is the fourth week, and based upon the previous last 3 weeks or over these 21 days, we will today discuss about more in depth about dislocations. We will discuss about dislocation nucleations, then multiplication of dislocations, then dislocation grain boundary interaction, a little bit of strain hardening, which we have learned also in the previous session. Solid solution strengthening or solid solution hardening, and something called as the quadral atmosphere at the E point phenomena, and even the E point hardening. So what is so let us get started. Okay, so what are dislocations? So why exactly do we need to study dislocations? Because dislocations can give us information about the properties of materials. It can indicate the properties of materials, and what type of material properties? Mainly the mechanical properties of materials, which are which is the foundation and very important in engineering and metallurgy and everything. So dislocations lead to mechanical properties. So that is why it is very important to study dislocations. Now, so this is something which we have learned previously. So I will not go into more. The dislocation interactions lead to work hardening. The equation which describes this is called as the Peach-Kohler equation. Peach-Kohler relation can be used for one-to-one dislocations. Okay, so let's focus. Let us start from here. So if we have a crystal, if we grow a crystal like a freshly grown crystal, then will it have dislocations or will it not have? Means will it be defectful? So what is seen is that even if we grow a single crystal freshly, still dislocations are present. So dislocations are present even in freshly grown crystals. Why? Due to internal stresses. And this internal stress can be caused by many factors. It can be due to temperature gradient, it can be due to the presence of impurity, it can be due to change in lattice structure parameters due to the impurities, and dislocation density. So dislocation density means what? Amount of dislocations per unit volume. So this is the definition of dislocation density. So what is the definition of dislocation density? Dislocation density is the number of dislocations per unit volume of the material. And dislocation density in freshly grown crystals ranges from 10 to the power 9 to 10 to the power 10 per meter square. So here what is important is the units. What is the unit of dislocation density? It is per meter square. So how is this coming? So dislocation, the unit is meters, it is the unit of length divided by the unit of volume, which is meter cube. So in the numerator we have meter, in the denominator we have meter cube, so then it comes out to be meter per meter square, or to the power minus 2. So this is the unit of dislocation density. So this is a so this picture you see, so this is a what so this is a magnesium single crystal, and in the magnesium single crystal, so we are simply looking at it along two different planes, so that is why there are two different these different planes, but we are looking at it at 0% strain. Okay, so even at 0% strain, what we are seeing is, so these are optical images. So what we are seeing is that in this magnesium single crystals we have speckles, which are nothing but attributes from dislocations. In a perfectly grown, freshly grown magnesium single crystal also we have this dislocation features. So dislocations are present in freshly grown crystals also, and it is these dislocations which are present in a crystal even before any kind of deformation or any kind of plastic deformation. Okay, so this is the important feature of dislocations. So now we will talk about the dislocations formed through plastic deformation. So let us assume that we have the perfect crystal. Okay, so if we have a perfect crystal, then if we so assume at first that we have the perfect crystal, then in order to have the first dislocation, we need to have the nucleation event, or in other words, we need to trigger the nucleation event. Now there are two models of this of how we can describe the nucleation. Nucleation of what? Nucleation of dislocation. So there are two models. So first is the homogeneous nucleation model, and the second one is the heterogeneous nucleation model. So we will look at that one by one. First we will talk about the homogeneous nucleation model. Okay, so we will go through this one by one. So let us first look at that title of this slide. So it is the homogeneous nucleation model. So homogeneous nucleation model assumes that what we are beginning with is a perfect crystal. We are beginning with a perfect single crystal which does not have any dislocations. Okay, then the energy of creating a small dislocation loop of a radius of a certain radius r in a perfect crystal is given by this equation. So this is the energy. Energy of what? Energy of creating a small dislocation loop in a perfect crystal. So this equation has two parts. Okay, what is the first part? The first part is you can see 1 by 2 GB square R, then ln, and means in the first part we have R and we have 2R in the log part, right? And in the second part we have what? We have R square. Okay, so remember what is R? R is simply the radius of the distribution loop. So the first part of this equation describes the increase in elastic energy, okay, during the creation of the dislocation loop, and the second part describes the work which is done by the applied stress in order to create a dislocation loop. So the first part is the increase in elastic energy and the second part is the work done by the applied stress. So as R increases, means as the dislocation loop grows in size, as its radius increases, then initially the energy increases and then decreases. Okay, so because of this, because the nature of the equation is such. Now, if we do the differentiation, then we can obtain the critical radius and the maximum energy. Okay, so if we do differentiation, we will get the this maximum energy. Now another thing which we will assume, that there is no thermal activation. Then nucleation can only occur when this EC, the different, after doing differentiation, so this energy is equal to 0. So if we put that in this equation, then the tau means the stress. The stress comes out to be G by 10. Okay, so G is what? Is the shear modulus. So now when this solved an assignment problem based on this, right, in the previous week. So now if we try to test this from this relation, if we try to test this on real example. So if we take the example of aluminium, so aluminium metal, so what is the shear modulus of aluminium? It is 25 GPa. Okay, so if we have capital G equal to 25 GPa, then G by 10 is equal to 2.5 GPa. Okay, theoretically it is coming. However, we do not see aluminium, we do not see 2.5 GPa strength in case of aluminium. If we grow pure aluminium, so pure aluminium, the shear strength exhibited is of the order of 0.01 GPa, 10 MPa, whatever. So 0.01 GPa, which is orders of magnitude smaller than 2.5 GPa. So then from this homogeneous nucleation model, what we are getting is not matching with the experiment, so we need something else. Thus, the conclusion from here is that the homogeneous nucleation model cannot explain why we have so many dislocations in the plastically deformed metals, because at normal temperatures and pressures, we have so many dislocations, so it cannot explain because the shear stress required for the nucleation event is so high that it cannot exist at room temperature. So then we come to the second model. Okay. So now we come to the second model, which is the heterogeneous nucleation model. So what we have in the heterogeneous nucleation model? So in the heterogeneous nucleation model, so this heterogeneous nucleation happens when there exists stress concentration from impurity particles. So we have to first assume this. So now let us first assume this, that this is a cylinder and this direction. So so this is the direction of the Berger vector. So in this direction, and this is the intersection. This is the intersection with the spherical impurity particle. Okay. So this is the intersection with the spherical impurity particle, and we have the small loop at the surface of inclusion. Okay. So now if there is there is an interaction, and then what will happen is that this loop, it expands around the Clyde cylinder. Means since this is the Berger vector, the dislocation will glide along this direction, right? Because this is the direction of the Berger vector. So we have this now. So this is the stage B. And then finally, when it separates fully, so what we get here is the prismatic loop. So this C, so this is the prismatic loop, and the shear stress required, so in this heterogeneous nucleation model, comes out to be G by 33. Now again, if we put this for aluminium, we have that aluminium has 25 GPa shear modulus. So if we divide it by 33, then we will see that it is 0.8. So it has reduced from 2.5 to 0.8, but still it is not matching with what is observed experimentally, which is 0.01 GPa. Hence, the heterogeneous nucleation model also so by this heterogeneous nucleation model also we cannot explain the large number of dislocations after the deformation. So in order to successfully explain the strength of metals as well as high density of dislocations observed after the plastic deformation, we need another model, and this is where the multiplication of dislocation, or the dislocation multiplication model comes into the picture. So what is the dislocation multiplication model? So let us start with the most widely used multiplication dislocation model, which is the Frank-Reed source. Okay, so here we have these 2 points A and B. Okay, so these are pinned, and one second, there is a spelling mistake here, I think. So we are here. We are at in the dislocation multiplication model. So how we came? We were at first. So just for a quick recap. So we are at the homogeneous nucleation model where it was not matching. Then we came to the heterogeneous nucleation model. So what happens in the heterogeneous nucleation model is when applying a large shear stress, a dislocation when applying a large shear stress, the dislocation. So if you see my pointer, so when applying a shear stress, some shear stress, then the dislocation can nucleate at the interface of the particle and the impurity, right? And then when it grows, and then it leads to this prismatic loop. So here also was not matching. So then we come to the dislocation multiplication model. So here what we have, so if you see, so this is the slip plane, and this region from A to B. So this region is this is the only part, means only this part from A to B. It lies in the glide plane. Okay, so and these are the dislocation lines. Okay, so this line and this line, so these are the dislocation lines. Which are out of the plane, this one and this one. Lines, these are out of plane, and only this part lies in the glide plane. Okay, so this dislocation segment is, so if when stress is there, what happens is this dislocation segment in between, so this part, this part can go out such that the points A and B, these points which are pinned down, they can act as dislocation source for multiplication. So how? So we will understand this. So what is happening? So this point we have L, so it is the same as I showed here. Now after applying the stress, the dislocation line can go out more and more. So from here, from C we are going to D, from D we are coming here to E. So as it bows more and more, then it so this is what this is like a semicircle, and then when after this point, when it is very close, then after the point E, so it will simply join, it will coalesce and form a loop, and the remnant part now becomes the origin of a new dislocation. Okay, so this is called as dislocation multiplication. This is the dislocation multiplication model. Now this process can continue operating and produce more and more dislocations from a single source. So this is called as the Frank-Reed source model of multiple dislocations. So this process can continue operating to produce more and more dislocations from a single source. So this is called as the dislocation multiplication model. Now what is the shear strength? Now what is the shear stress required in this case? So here the equation is GB by L. So what is B? So B is the Berger vector, and L is nothing but it is approximately 10,000 times the Berger vector. Now if we apply the same for aluminium, so pure aluminium, so we see that since aluminium has 25 GPa shear modulus, then the predicted strength becomes 0.025 GPa, which is very close to 0.01 GPa. Hence the it is matching. Hence the dislocation multiplication model can kind of successfully describe the shear stress required. So in addition to the dislocation multiplication model, so there is another thing which is called as the dislocation grain boundary interaction. So previous thing was for the single crystal materials. Now what about the polycrystalline materials? So in so what what about the polycrystalline materials? In case of polycrystalline materials, grain boundaries can also act as dislocation sources. So if we have a grain, so if we have a domain, and then this is the, so this part is the boundary, right? So this part is the grain boundary, and if this is a dislocation source and the dislocation is moving in this direction, then when it encounters the grain boundary, then this dislocation motion is stopped. So what happens is this dislocation is blocked by the grain boundary, which creates a stress field in the neighboring grain, means in the grain which is next to it. So then the in the adjacent grain, so this location will be blocked by the grain boundary, and which creates a stress field in the neighboring grain. The stress field will lower the energy barrier for dislocation multiplication. So this stress field will lower the energy barrier for dislocation multiplication from that part of the grain boundary, making the grain boundaries effective sources for dislocation. So this is the dislocation grain boundary interaction. Now we come to strain hardening. So we know, so this is stress strain, right? So this is the strain. And this part is the stress. Okay, so this is the elastic region, right? This part is the this part is the elastic region, and this is the what this is C R S of the critically resolved shear stress. So this part is the this part is the elastic region. Then we have the stage 1 and stage 2 and finally stage 3. So in stage 1 what happens? So in the stage 1 the dislocations can glide easily, so there is low strain hardening. However, in stage 2 these dislocation interactions start, and these are not mild, these are strong dislocation interactions, which gives rise to large or high strain hardening or large strain hardening in case of stage 2, which is this stage, and this stage 1 is this stage. Now we come to the next topic, which is the solid solution hardening. So before understanding solid solution strengthening or solid solution hardening, so we will first understand that what are solid solutions. So this one, so this is a perfect lattice or a perfect crystal. Okay, so this is a perfect lattice where all the atoms are sitting on the lattice positions. They're perfectly ordered. Now if we see, this is a perfect. This is a perfect lattice. Now if we squeeze, so this is not a solid solution, this is perfect lattice. So from here the solid solutions start. So if we squeeze a foreign atom into the matrix called as the interstitial atom, then there will be a stress field around it, there will be a distortion or a lattice distortion. So this one is called as the lattice distortion by interstitial atom in a solid solution. So this is interstitial solid solution. So this one is and these two, so this is interstitial solid solution, and these two are called as the substitutional solid solutions. What does it mean? It means that there is a substitution or a replacement of any host atom by a foreign atom. Now the foreign atom which is replacing the host atom, it can either be smaller than the host atom or larger than the host atom. So the foreign atom, the foreign atom can either be smaller in size than the host atom, or it can be larger in size than the host atom. So if the foreign atom is smaller in size, then it is called as the small atom substitution. If it is larger, if the foreign atom is larger in size, then it is called as the large atom substitution. So both fall in the category of substitutional solid solutions. So we have interstitial solid solutions and substitutional solid solution. And in both cases there will be lattice distortion. So either it is interstitial solid solution or substitutional solid solution, so there will be a lattice distortion. Okay, so why will there be distortion? So if we have, so this is a representation of an interstitial solid solution. Okay, so we have this was the host lattice, and in between these are the interstitial atoms. Okay, now this is the interstitial one. Now if we look at this, so what is this? So this is the representation of a dislocation which is stopped by an interstitial atom. So this was the extra half plane, and it is moving in this direction. So what happens is, as when it came here, so then it got stopped. So this is the representation of a dislocation stopped by an interstitial atom. What is happening is the strain field which is imposed by the, so here they are assuming that the foreign atom is coming from the solute, hence everywhere it is called, it is written as the solute atom. So what is happening is the strain field imposed by the solute atoms interact with the strain field of dislocations. The strain field which is imposed by the solute atoms interact with the strain field of the dislocations, hindering the free movement of the dislocations, and this leads to strengthening. So the strain field imposed by the solute atoms will interact with the strain field of dislocations, hindering the free movement of dislocations, leading to strengthening. So if we compare the interstitials versus the substitutional, then which one will cause more hardening, and what will be the reason for that? So what we see is that interstitial solute strengthening is more effective than substitutional solute strengthening. So what we see that interstitial solute strengthening is more effective than substitutional solute strengthening. Now why? Because of the simple reason that the stress field caused by interstitial solute strengthening is more than that of substitutional solute strengthening. Okay, the stress field caused by interstitial solute strengthening is more than that of substitutional solute strengthening. Now if we simply compare two atoms like FCC and BCC, then what we see, so at first if we look at FCC, then the interstitial atom sits in the octahedral void or the octahedral site. Okay, so in case of FCC, this is the interstitial atom, so it sits on the octahedral site. This leads to a symmetric stress field, and there is a certain amount of strengthening. Versus if we compare this with BCC, then we see that the interstitial atom does not sit on the octahedral site, it sits on the tetrahedral site. So here the octahedral site is by this one, 2. So this is these four are in plane. So this is 1, this is 2, this is 3, this is 4, and these two are out of plane. This is 5, this is 6. So this is the octahedron and this is the octahedral site, and here this is the tetrahedral site, right? So this one is back, this is in the front, it's in the middle, and this is the outer. So this here this interstitial atom is sitting on the tetrahedral site, which if you look at it, you can understand that this one is symmetrical, whereas this one is asymmetrical. It is not symmetric. Hence, this will give rise to an asymmetric stress field, and that will cause more strengthening or substantial strengthening compared to the octahedral one. So here, so this is very easy. So it's just what is the stress necessary for plastic deformation increases due to. So you know the answer we have discussed in previous one. So it's because of strain hardening. Okay, so now we will come to the quadrille atmosphere and the yield point phenomena. So first we will start with this. So this is again a simple stress strain curve. So this is sigma stress, this is epsilon, so this strain. So we see this part, so we know what is this part. So this part is the elastic region. So then from here to here we see the zigzag point in the currents. From here there is plastic. So what is this point here? Okay, so this is the yield point. So what is the what is yield point and what is the cause of this yield point phenomena? Okay. So what happens is, so up to this point, as we were increasing the stress, the strain is increasing. So suppose we are applying, so we are doing a tensile test, right? So we are stretching, we are doing a tensile test, and as we are increasing the stress, the strain is increasing. Now at some point what will happen, there is a certain drop, there is a certain drop in the stress strain curve followed by this zigzag part. So this point is called as the yield point. Okay, very specifically there is a upper yield point and a lower yield point. Now, and this phenomena is called as the yield point phenomena. Okay, so what is the cause for this yield point phenomena? The cause for the yield point phenomena is the interaction between foreign atoms and dislocation. So this is very interesting. So initially we had a lattice, so a perfect lattice, so there is nothing. Now if there is an introduction of dislocation like this, then the lattice planes of the dislocations result in widened zones. Okay, so this is called as the dilation. So the lattice planes of the dislocations the lattice planes of the dislocations result in widened zones, which are known as the dilation zones. Okay, so dilation zones. So in this energetically favorable zones, what happens is foreign atoms are preferably deposited whose accumulations are called as whose accumulations are called as quadrille atmospheres. So this is the quadrille atmosphere. Now what happens is, these foreign atoms first prevent the dislocations from moving. So this is called as the pinning of dislocations. What happens is that collection of the solute atoms at the dislocation site relieves the stresses associated with the dislocation, which lowers the energy of the dislocation's presence. Thus, moving the dislocation out of this quadrille atmosphere constitutes an increase in energy, so it is not favorable for the dislocation to move forward in the crystal. So as a result, the dislocation is effectively pinned by the quadrille atmosphere. So this is the yield point. So only at the certain stress the dislocations can break away from the foreign atoms and the plastic deformation begins. Once the dislocations have come loose, then they can move with very little effort. So that is accompanied by a reduced force and the stress drops briefly. So this is this point where the stress drops briefly. Now, when the dislocations encounter other obstacles, they will get deepened again. So this corresponds to the zigzag part of the curve. And when the dislocations have moved through the microstructure and are no longer pinned by the caudal atmosphere, then the stress has to be increased again to achieve further elongation. So it is this part. So remember here the rate of diffusion of the foreign atoms or the solute atoms and the velocity of the dislocation. So these two have a crucial role in determining whether we will get this part of the curve or not. So where this part of the curve is called as the yield point phenomena, the yield point hardening, and this is called as the Luder strain. Okay, so thank you everyone. So I will close this session. Now if you have any questions, you can post the questions in the SOAM portal in that NPTEL course, and I will be happy to answer.